First of all, when you got your key, were you like, what's that bad boy doing there? Were you like, what did she do with that? We'll get there. All right. A particle moves along a line so its position at any time t is greater than 0. So we're talking about time. There's no sense in having a negative time, obviously. So its position in terms of time is given by that function. That's an interesting function because it's a cubic function. So immediately when you look at that function, you'd be like, oh snap, when I take the derivative, I get a quadratic. When I take the derivative of that, I get a linear. So instead of having that constant, acceleration, now you have your acceleration is linear. So that's kind of cool. So when we take the derivative of position, we get velocity. We take the derivative of velocity, we get acceleration. And that's just plain taking the derivative. When we're talking about this particle at rest, it is at rest when the velocity is equal to 0. So I set this velocity equal to 0, and it didn't factor, or maybe it does, and I was too lazy. I gotta tell you something. If it doesn't pop into my head right away, I jump right to the quadratic formula. Anybody else like that? Did you all factor it? Because it's a quadratic. So my velocity, and remember when we talked about the ball going up and down, when that velocity leaves my hand, when that ball leaves my hand, its velocity, its speed is as great as it's going to be. It loses its speed as it goes up, and then once it changes direction, it starts to build speed again. So speed is the absolute value of velocity. Velocity tells me when things are moving in a positive or negative direction. But its speed is equal to 0. Its velocity is equal to 0 when it's changing. So it takes what I give it, it runs out of that kinetic energy and stored down. And then as it comes down. And it's gaining speed as it drops. And it's gaining speed at a constant rate. So I set it equal to 0, and I get my two values for t. So it is at rest those two times. That's when it's changing direction. When we talk about displacement of the particle for the first 3 seconds, I went ahead and I put my original equation into my graphing calculator, that guy, into my calculator, and I just went ahead and went to the table of values and recognized that at the start it's here, at 3 seconds it's here, so its displacement is going to be 15 meters in a positive direction because it's positive. A rock is thrown upward from a 7-meter alien. He's 7 meters tall, so that's where the rock is starting. I guess he's holding it on his head. At a velocity of, here's your velocity here, that's the push, 48 meters per second, and it reaches a height of, this is my output with this equation, meters in 2 seconds. Today we're going to do an activity where we're really focusing on rates and their units, so I want you to make sure you're paying attention between what units. That helps us know what goes where. When I'm finding the rock's velocity, I take the derivative. Acceleration, I take the derivative again. Pay attention to how I'm labeling these. If I wanted to call this S prime, I could, or S double prime, I could. But we want to make sure that we're understanding our labeling and our units. How long did it take the rock to reach its highest point? So I did this 2 ways here. Here's the algebra 1 way. In algebra 1, we know that the vertex is negative b over 2a. So I went ahead and found negative b over 2a. but I'm talking about it, the rock reaching its highest point. That's going to be where, that velocity is equal to 0, where it changes direction. It's easier with the calculus. All right, the particle P moves on a number line. This graph shows its position as a function of time. So this particle moves to -1, then it moves to 1, stays at 1 for a while. It moves down to -2, moves up to 9. If we're talking about displacement, the particle never really got anywhere. Do you see how it started and stopped at the same place? It went up and back and up and back and up and back on the number line. Show the number line. So if this is my particle, it moves down to -1, and it moves up to +1, sits there for a while, and then it moves down to -2, and it comes back up to 0. That particle bounces back and forth on this number line. It doesn't really get anywhere. Does that make sense to you, displacement? And you can talk about when it's moving to the left. It's moving to the left as it's moving to -1, right? So this is its position. It's moving to the left, it's moving to the right, it's staying still, it's moving to the left, it's moving to the right. So it's moving to the left when my derivative is negative. It's moving to the right when my derivative is positive, and it's standing still when the slope of the tangent line is 0. Everybody okay with that? Turn to your group and talk about one thing from this that you get and one thing that you're still working on. Turn to talk, go. Flip it over. So Nadia asked a great question. She's like, Nadia asked a great question. She's like, I'm not sure this matches what was on the notes. So I took a good look at it and I'm like, oh, be careful of what it is you're looking at. This is a graph of the velocity. This is a graph of position. Are they the same thing? This is a graph of the rate of change. This is the graph of the slope of the tangent line. This is the graph of slope. So when we're looking at this is the graph of the velocity. This is the rate of change. Velocity is your change in v is equal to the change in s compared to change in t of a body moving along the coordinate line in meters per second. So when does that body reverse direction? Careful here. It's not here. This is not where it reverses direction. Because we're talking about the slope of the tangent line. This is where my slope is its steepest. Ooh. Steep slope. Not so steep slope. So this curve is going up, right? Slope of 1, slope of 2, slope of 3. This curve is going up like this. This is where it's at its steepest, right? Now what's happening is it's still increasing, but it's increasing at a decreasing rate. That means that its rate of change is getting smaller and smaller and smaller and smaller and smaller. What happens here? This is where my velocity is equal to 0. This is where my particle runs out of energy and starts to fall. So that's what happens here. The particle reverses direction when my velocity is equal to 0. This is a graph of the rate of change. I don't think you've ever seen one of these before. In physics? So this is the graph of the rate of change. This is where the velocity goes from being positive to negative. If we're talking about speed, we would need to take the absolute value of this, because here my particle is speeding up. It's going faster and faster and faster and faster and faster and faster. Its rate of change is -1. Its rate of change is -2. Its rate of change is -3. Faster, 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 while it's falling. When is the body moving at a constant speed? There's no change in the speed. It's going 3 meters per second this whole time. Constant rate of change. Its speed is not changing. Now its speed is decreasing at a constant rate, because this is a linear section. So it's decreasing, speed is getting, his velocity is getting, he's going slower and slower and slower, but at a decreasing rate. Changes direction again. What is his maximum speed? Whether you're talking about this 3 or these 3, it's 3 meters per second. When we're talking about speed, nobody cares what direction, just what is the fastest that he went. At what time is he slowing down? You are slowing down when your velocity and your acceleration have the opposite sides. Here my velocity is positive, here my velocity is negative. Here my acceleration is positive, my acceleration is negative, my acceleration is constant, my acceleration is positive. So anytime I have a positive slope and a negative velocity, I'm slowing down. Anytime I have a positive slope and a positive velocity, I'm speeding up. So I'm speeding up, I'm slowing down, I'm speeding up, I'm not changing my speed, I'm slowing down, I'm speeding up. Walk your partner back through that. Drag your pencil along this and talk about when you're speeding up and slowing down. Go. Walk your partner through it.
So the further away you are from 0, the closer you're
So when it's like the x-axis and it's the positive slope.
All right, so looking at today's notes, we're going to talk about rates of change in contexts other than motion. You know the slope between 2 points is your change in your y values compared to your change in your x values. I would like for you to get used to that concept of this being our dependent value or variable, and here's our independent. So whenever we're talking about the slope or the rate of change between 2 points, we're talking about that rate of change. What happens to our dependent variable compared to our independent. And something to make sure you can understand, and those conversations between science is so huge, because this is what goes into your function, and this output here is what comes out of your function, and this is what you're measuring. This here is what you're measuring compared to this. So when you're talking about your changes in your output compared to your input, that has so much to do with what we talk about science-wise. And we're talking about what it is that we are measuring. Okay. So when we start talking about the derivative, we need to make sure that we understand that this here, this x is your input, and this f of x is your output. And when we're talking about the units for the derivative, and that's what this big conversation is today, is all about units, we want to make sure that we have the units for your output or your dependent variable. And this here is a per. Sometimes we talk about it being a for every. Sometimes we talk about it being an out of. But that line that represents division is a huge conversation, because that's what gives us that ratio. That's what gives us that comparison of two numbers using division, and it's going to be compared to our units for our input or our independent variable. So when we teach this in Algebra 1, we make sure the kids understand that your input is your independent variable. And they like how that matches up. All right. If your derivative, and every time you see this, I want you to think about your rate of change. It's the slope of the tangent line is the derivative. If your derivative is bigger than 0, and I want you to think about this as your function. And sometimes I like to refer to that as your story. That's going to be increasing. If your slope or your rate of change is positive, then that means that whatever's going on in your function, whatever your story is, it's increasing. And increasing can be moving up in the air. Increasing can be moving right on the number line. Increasing, getting bigger. If your derivative, which is also your rate of change, your slope, is less than 0, and make sure you understand when we talk about greater than 0, that's a positive value. Less than 0 is a negative value. Then your story, your function, your situation, your output is decreasing. You can put the word output here too. It's so funny. We work on teaching you guys functions and stories and those relationships from day one of algebra, and it really is. You could ask so many, like, what is a function? It's one of those things where you're like, well, I know what it is, but I don't know how to say it. Or I know what it is, but I don't know how to describe. Like, well, it's that thing. Well, you know. What is a function? All right. Sometimes our functions will already be a rate of change. With your group, talk about and see if you can conceptualize verbally, translate from math language to English language. see if you could translate what this represents in this story and what this represents in this story. Turn and talk, go. Okay, so if I'm talking about a rate of change, if my function is the bunny population after X number of years, then my derivative, my slope, my rate of change, is going to be the rate of change of the bunny population in X number of years. How much did my number of bunnies change compared to how many changes happened per year? That's the easy one. How is this second one different from what we asked on the first one? Yeah. Yeah. So remember when we talked about how I can have the derivative of position as velocity, I could write that as v of t. And you have to know, oh, that's the rate of change of that position. So you have to pay attention to which graph are you looking at. Nadia's like, I don't understand. This is different from what you said. I'm like, because this is a graph of a rate, and this is a graph of position. So reading these stories, we're talking about this is my original function. What is the change of the bunny population? If this is the rate at which the bunny population increases the number of bunnies per year, I'm looking at the rate of change of the rate of change of the bunny population. Ready for this? Per year. Rate of change. So I'm looking at the rate of change of the rate of change. It's what we talked about with acceleration. How much is the velocity changing? That's acceleration. It's the rate of change of the rate of change So I'm talking about the change in the number of bunnies per year, and we end up talking about that as per year squared. The rate of change of the number of bunnies per year, and we talk about that as per year squared. You know the triangle means change, right? Not everybody knows that. That'd be terrible if you're copying down my notes and you're like, why are there triangles? She must have been confused thinking about geometry. All right, let's talk about this. Miss Holdaway wants Mrs. Glazer to finish creating review games. The number of games Mrs. Glazer has completed is modeled by G of W, where W is measured in weeks. With your group, go ahead and interpret A and B. Marcus Echo.
The rate of change of the number, okay, the rate of change of the number of
So when we do these problems, it's easier if we all train ourselves to think using a certain template. And it's smart if we start talking about our input value first. So if I'm looking at G of 10, if I'm talking about after 10 weeks, at 10 weeks, I've made one game. After 10 weeks, I've made one game. When we talk about the derivative, interpret the derivative in context of the problem, after 9 weeks, I'm making 2 games per week. So I'm pretty sure we need to do a better job with our numbers, because if it takes me 10 weeks to make one packet, at 9 weeks, I'm not making, or game, I'm not making 2 per week, you know what I mean? So that's a little illogical. Let's talk about Fairfax County sending email updates on weather and COVID. The rate at which Fairfax County sends an email update per week is modeled by M per T. Stop. Is it a position? Is it an original function? Or is it an equation of the rate? Do you see the rate? So the rate at which Fairfax County sends an email update per week is modeled by that, where T is measured in number of weeks. Start with the template. After how many weeks? After 3 weeks, the rate after 3 weeks, the rate, well, let's start with, I keep wanting to jump to the rates. FCPS is sending what? How many? 15 emails per week. So because this is already given to me as a rate, here it's not. Here, this is an input output, 10 weeks, 1 packet. After 9 weeks, I'm making 2 games per week. This is already a rate. After 3 weeks, Fairfax County is sending 15 emails per week. This is an XY ordered pair. This is a rate of change. Rate of change. Okay, now I need the rate of change of my rate of change. Start with the after. What's the template? After how many weeks? 4 weeks. FCPS is sending what? Five. After 3 weeks, FCPS's, wait a minute, we need to include the rate. Hold on. FCPS's rate is increasing. That's what it is. Increasing by 15 emails per week. That's what that needs to say. Because here, wait till you see this one. FCPS's rate of emails. How do I know it's increasing? By 5 emails per week. Okay. Let's talk about what this means. By the 3rd week, FCPS's rate is increasing by 15 emails per week. After 4 weeks, FCPS's rate of emails is increasing by 5 emails per week per week. So it's sending 15 emails. That's my rate of change. And that's going up by 5 emails per week per week. That means that is how much it's increasing as I'm going. My rate is not constant. My rate is increasing at an increasing rate. Right, so on the basic level, Fairfax County is sending out emails. If the rate of change of the emails is times 15, let's say week 1 they send 1 email, by week 2 it's going to be 15 times that, 15. Okay, by week 3, if that rate was constant, it would be 15 emails times 15 times 15. So 15 emails, 30 emails, 45 emails, and so on. But it's not constant because the derivative, this is the rate of change. It's changing by 15. But this is the rate of change of my rate of change, meaning that it's changing at an increasing rate. So it's increasing by 5 each time. So instead of increasing by 15, it's increasing by 20. And then it's increasing by 25. And then it's increasing by 30. And then it's increasing by 35. So what ends up happening is when we had our position velocity and acceleration graph, our acceleration, that last graph was constant. So our velocity was changing. That was gravity, 9.8 meters per second squared, right? It falls. That's what it does. And that rate of change wasn't changing. Because our rate was the original part of our problem, that's this story here. That's my rate.
So that's already like a derivative.
That's already a derivative. Here is a derivative of the derivative. So how quick is my derivative changing?
So like for that for A, that would be like a linear, like it's increasing but like linearly, and then for B it's like exponentially increasing.
It wouldn't be, no, because as you take a derivative each time, you lose a power. So my original function would have to be cubic, then quadratic, then linear, then constant. So each time you take the derivative, you drop a power, right? So that's why when we talk about position with the ball, it was a quadratic. Second power, velocity was linear, first power, acceleration constant, no powers of x. Make sense?
How would you know it's cubic?
You don't, because we weren't given the original function. I just know that this rate, whatever the equation is that models it, when I take my derivative of it to find my acceleration, it's 1 power less. But then I need to remember that it's the rate of per week per week. So I'm looking at the rate of change of my rate of change. Does that help?
Yeah.
Yeah.
What do I write down in 2A?
Say that one more time.
What do I write down in 2A?
What do you write down for what?
2A.
2A. After 3 weeks, Fairfax County's rate is increasing by 15 emails per week.
Okay, thank you.
Okay. So we need to start paying attention to whether our rate of change is increasing or decreasing. And that totally has to do with whether or not that derivative is positive or negative. So to know if something is increasing or decreasing, you're going to check the sign. Of the derivative. So height is increasing if, when you take the derivative of the height, if it's greater than 0. Velocity is decreasing if the derivative is less than 0. Hardin High School's population is increasing if, when you take the derivative of it, the rate of change is positive. Anything that you find, and we can call it a happy face, taking the derivative, if it gives you a negative value, it's decreasing. So we need to make sure that we're understanding that that derivative is that rate of change. We can use a table of values to help us estimate things. With your group, talk about the rate of change of people per year. Estimated at 15, estimated at 20. Rate of change, you mark a second. All right, when I'm estimating the rate of change, I'm looking at the rate that the people are changing compared to the rate that the years are changing. So my people, if I'm estimating it for 15 years, that's going to be somewhere up in here. So that means if I have 150 people after 20 years and 120 people at 10, my rate of change is going to be 30 over 10, or 3 people per year. Do you buy that? Now when I have P of 20, I have to make a story about what's going to happen on either end. So you actually have 3 choices of how you could do this one. You could go ahead and estimate 30 and find the average between 30 and 10. You can do the average between 30 and 20. Or you can do the average between 20 and 10. You can't just say at 20 because that doesn't help you with what the average is. So if you do 30 for 10, you've got, what's that, 80 over 20? So that's 4 people per year. 30 over 20 gives me 5 over 10, so that's 5 people per year. 20 over 10, we just did here, right? Make sure you do this in your notes so you remember what it is that you did to be able to find it. All right, a store is having a 12-hour sale. The number of shoppers who have entered the store T hours after the sale begins is modeled by the function E, defined by this for that. At what rate are the shoppers entering the store 5 hours after the start of the sale. What are you gonna do? 12-hour sale, so here I have T from 0 to 12. The store is having a sale, so the total number of shoppers, am I looking at this equation being my rate or my number of shoppers? My output for this is my number of shoppers, right? So if I want to know my rate, what do I have to do to this? I need to find the derivative.
Oh, yeah.
So my rate of shoppers, my equation is going to be 14 times 3 is 54? No, 52? 42.
It's 220T, right?
Didn't, oh, thank you. Everybody okay with our store having the sale and 200 shoppers per hour? Because they're asking me for the rate, I needed to take the derivative. The rate at 5 hours. 5 goes in here. Here's the most important part. You want to make sure that you include your rate. So 200 shoppers per hour. So it's not like I've had a total of 200 shoppers. If I wanted to know the total number of shoppers who have entered the store, this equation would give me the total number of people that have come in. This is telling me how many people are coming in per hour. This is telling me the rate. See the difference? So make sure you include that derivative. All right. This one's backwards because time is our output, not our input. I'm measuring how much time. So time is not an input value like we had with the ball being thrown. In this example, I'm measuring time in days for this pond to evaporate. So my input value, my units for my input is what? How am I measuring my pond? My output value, how am I measuring my output? So I'm looking for, if I was talking about f of p is equal to t, this t, that's my output value. So my f prime of p is going to be equal to my days per liter. What are the units for my rate of change of my rate of change? What do you think? Days per liter per liter. Or you could call that days per liter squared. The temperature in degrees Fahrenheit of a lake is the differentiable function W of time. The table shows the water temperature is recorded every 5 days over a 20-day period. Use the data from the table to find approximation for the rate of change at 10. Show the computations led to your answer, indicate units of measure. So if I'm looking at my temperature as a function of temperature in degrees, that's my output. So W of T is going to be equal to my degrees. I'm measuring my degrees per day. If I'm looking for the derivative, I'm looking for the rate of change of the temperature per day. If I was looking to see how that rate of change was changing, that would be my second derivative, the degrees per day per day. But we're not doing it per day, we're doing a degrees per day. I'm looking for an output for 10 days. Why can't it be 61? Why can't it be 61 degrees? Say that again? That's the total. Yeah, that's how hot or cold it is. I'm looking for what? The rate of change. So if we want to know 10 days, talk about with your group what might be a good approach. So in your homework tonight, I really want you, now, we didn't get time to do our game. Did you want to do a game? We'll start with our game next time. I really want you.
Why is Tom not on the top? Is it kind of the,
Because this is my input, this is my output. So it's changing your output compared to your input. So for this one, my input is days, and I'm measuring my degrees. I'm measuring my degrees Fahrenheit. So I'm measuring my degrees per day. Up here, I was talking about and measuring how many days per liter of water. So this days is up top. It all depends on your input output. Does that make sense, Kara?
yeah.
All right, so if I see you on Tuesday, you'll have a quiz.
What about
If we go virtual, check Schoology. Okay? Yes, okay? You have 10 minutes to start. Are you going to take advantage of that opportunity? Do you want to start now? Sure. Give me a minute to find a copy of this.
The packet's due today, right?
Yeah, if you have your packets, your projects, you can turn that in.
We don't need this for this, right? Like when I just put that, like meters per second. Is that needed there?
Yeah, because
Okay.
that's what it is.
I
Your
thought, but I
graph.
wasn't sure.
Yeah.
And then we don't need them for the equations, right? Like this part?
No.
Okay.
Pete. A or B? Here's A.
Miss Glazer. Last estimation, I could turn this in electronically. I emailed
Yeah.
it to you. Is there a better way you wanted me to do that, or just email?
No, I got it. It's perfect.
Awesome.
No worries. Thank you.
When is the next one?
Ideally, by here.
And the unit 4 and 3 sheets, the back. Yeah, for the homework.
Unit for
The
the back of that, that's for a second quarter. That needs to be turned in by that day too.
Is this due today?
Yes.
Then if you want to show up. Yeah, Remy and I are gonna build the route this evening.
So I would love to fill out your survey, but that's exactly the problem. Both of my classes, both of my preps are first and second period, so I never have to deal with the 22.
Theory. It's not
So
that
I think it's
training.
wonderful. How about that? No. No, I'm frustrated by it because I see kids, when I go for a walk to check in on either my mailbox or whatever, I see kids hanging out at the turning table, having a good time, not with no urgency to get to class. And then I see them strolling with their green passes, not caring. So it's a frustrating thing, experience for me. But if you want me to write that in your survey, I will, but I don't have kids that come. Yeah. Yeah, that's fine. I've got it.
It's a good idea. Joseph designed like a mechanism where the
Yeah.
It's also very nice to have. So it's nice to have the black input, the even. So now you just 3D print more.
No, it's kind of like water, right? So every time you take the
It's like the kind of thing where you just do it and you just do it.
it's always
When you
so
apply,
that's,
you're just like,
so that's never gonna happen.
It's not a raw and it's also
Derivative
like.
of natural law is always this. So that's only
Yeah, like you
if
did.
it's up.
It's not a bad idea. I think Marcus is.
I'd rather mine. I showed them mine. I showed them mine. Yeah, I showed them mine.
I understand what you're saying,
It's natural law of the best.
but the advantage
They have
is that.
they have the thing is that everyone has them.
It lets us
So like,
like hold it
sometimes,
really basically.
like
That's something that I can figure out.
sometimes differential laws.
And it's like we started so it's fun. The service fund.
Yeah, you might want to like get rid of this. Yeah, you might want to know that plug too.
I have faith everyone was gonna work this time. I genuinely believe it's gonna work. I hope it works.
Yeah, cause that's fine, the equation of the 10.
I'm
You have to take that slope. Use, sequential
And also-
curves, so it would be y minus one.
But then it's
Oh,
not.
it's calling the pass.
That's the same thing. I'm still not even here. Really? I've been. No,
Yeah, but it's within.
and it just be like, you'll see.
Yeah, I'll come over.
And how do you want to do direct
I already do that at home. That's the thing.
If I were to come back, it would be.
I know there's problems. I don't think anyone's gonna fix them.
If my parents show up unannounced, I'm just gonna be like, I'm at the library.
Oh yes, I'm really hoping this draw will be like very good prototype and then like minor changes.
I don't even go to Raven. I'm scared to like ask like order things from them. So like, I'm just better.
I just love it. Being alone is like.
Well, that's not very.
I mean, I have my Skype.
You're not. I can't sleep.
No, if I go to VCU, I'll if I go to VCU, I'll move into an apartment. I mean, I think I have to do like a year in VCU.
There's a lot of colleges like freshman.
But like living with my brother.
Okay.
Yeah.
Is it first year? Is it the one that graduated last year?
Yes.
He was in Jan?
He was?
Oh, isn't he like Virginia Tech too? Virginia Tech is the thing is like massive public schools, so.
They should, when they have lots that happen.
VCU.
Like, it's like, it's just adding more.
Yeah, you can, because my brother takes because they knew he had a girlfriend. She went to UB. So they yeah, he would drive in 2 hours. So they knew it.
Hey, before you start packing up to leave, I wanna make sure you understand a couple of due dates. So I wanna make sure that you understand a couple due dates. So here's the next time I see you. And then we have this 2-hour early out short period, but I will see you here. Anything that you want, counting as the second quarter, has to be turned into me on this day. So a bunch of people are asking me, when are the IGTOBs due? I don't know. Do you want your curve? Do you understand what I'm saying? Because if you want your curve for the second quarter grade, and I'm not doing grade changes because I already have the grade in there. So I'm satisfied with the grade. But if you're not satisfied with the grade, you got to get this to me on this day. Are you okay with that? Are we clear? Go ahead.
Would the retake be after the quarter?
Yeah, so if you need a retake grade, we need to have that conversation here, right? Because typically I give you 2 weeks. And you just got them back. You got them back here, right? So 2 weeks would be, the retake deadline would be here for sure. Any other questions about due dates and deadlines? Okay.
I do.